Hey guys, this is Mr. Beckstrom, and today I want to go over a couple of problems from this section 8.3. So the first one here, it says use technology to find the p-value for the hypothesis test described below. It says that the claim is that for 12 a.m. body temperatures, the mean is, this is the mu symbol. Mu is less than 98.6 degrees Fahrenheit, and the sample size is n is equal to 5. And the test statistic is t is equal to negative 2.208. So let's kind of talk about what this is and how we can go about finding this. So remember that the test statistic, that's our critical value. That's that value that lies along the horizontal line of our bell curve here. So remember, just like the normal distribution, that t distribution, or sometimes called the student t distribution, is also a bell curve. That shape is based off of the size of the sample. So if we have a sample like this, the first thing that we want to do is see if this is a one-tailed or a two-tailed test, and we look at the claim for that. This uses an inequality here, not an equal sign, but an inequality that tells us it's a left-tailed test, which is a one-tailed test. If it's pointed to the left or if it's pointed to the right, that's a one-tailed test. So since it's pointed to the left, this is a one-tailed test. So we're looking for the area over here in the left tail. And this value right here, that's going to be our test statistic. That's going to be our t-score here, our t-value. And that value is equal to negative 2.208. Right? Now remember, the value right in the middle of the t distribution is 0. And it goes positive values to the right, negative values to the left. Way down here is negative infinity, but when you get even down to negative 10, the area under that curve is so small that it's insignificant. So if we're using some type of technology, we can just put negative 10 or negative infinity, and it doesn't matter because the area is so small that it wouldn't even show up. All right, so how do we find out what this little area in the tail is? Because whatever that area in the tail, that's going to be our p-value. Now, if we were doing a two-tailed test, if this was an equal sign, then we would have two tails. We'd have to find this area, and then we'd have to double it because we'd have the area on both sides. And we could double it because, like the normal distribution, the t-distribution is also symmetric. That means it's the same on both sides. But since it's a one-tailed test, once again, one-tailed test is less than or greater than, then we only have to find it on one side. And for that, we can use our calculator. So this is how we do it. We go to our calculator. We're going to go to second vars, which is our distribution. I'm going to go down to our t-CDF. So that's kind of like our normal CDF, but for our t distribution. All right, so my lower limit, that's going to be way down here, which is really negative infinity. But like I said, we can start with any small negative number. I always like to put in negative 9999. That's pretty common. Like I said, you can put in negative 10 even, and you're going to get the same result, just because anything less than negative 10 is just such a small area down there that it's just not going to show up in our findings here. Now the upper limit, remember we always go left to right, the upper limit is this value here, this t-score here. So that's going to be our negative 2.208. So these are our critical values on the horizontal scale that we're putting in there. Our degrees of freedom, this is important. This is the difference between the normal distribution and the t-distribution. And that is 1 less than our sample size. Our sample size here is 5, so we're going to put in a 4 and put that in. And that gives us that area in the tail. So out to 3 decimal places, that's going to be 0.046. So our p-value is going to be 0.046. And that is our p-value. So they didn't give us what significance level they were looking at, but if we were using a common significance level of 0.05, this would be less than or equal to that. So in this case, if we're looking at that significance level, we would reject our null hypothesis, which means that we would support this claim right here. All right, now let's take a look at the other question here. So just a minute, pull this thing up. And for this, I'm just going to show you how to put the whole thing into the calculator, and then we'll go over a quick rundown of the entire claim process and then how we go about supporting or not supporting our conclusion. All right, a data set about speed dating includes like ratings of male dates made by the female dates. The summary statistics are our sample size is 188, our sample mean is 5.85, our sample standard deviation is 2.14. We want to use a 0.01 significance level, which is the strictest one that we can use, to test the claim that the population mean of such ratings is less than 6.0. Less than 6.0. Assume that a simple random sample has been selected, identify the null hypothesis, the test statistic, the p-value, and state the final conclusion. All right, so what we do is first we're going to state the claim in symbolic form. So the claim is that the population mean, that's our mu symbol, is less than 6. So we're going to write less than 6. You can either write 6 or you can also write 6.00. Either one is fine. And then our null hypothesis, we're going to write that's the h sub 0. We always set that equal to our claimed value. And for the one-tailed tests, which this is, which includes where the claims are either less than or greater than, it always matches our claim. So the alternative hypothesis is less than 6.00. All right, now to put all this stuff in our calculator. So for this, I'm going to do a t-test. So for the t-test, I'm going to do stat tests. Go to t-test here. And I am going to enter. I'm using statistics, not data. Remember, if I was using data, they would have given me a bunch of actual data values that I would have put in my L1 or L2 list and used that, but they gave me the statistics here. All right, so let me go over here, and so this is my mu value, that's my claimed value, so that's just 6. My sample mean is 5.85. My sample standard deviation here is 2.14. My n is 188. This is a left-tailed test. And this is all of my stuff. So my I wish I could get that on the same page. But my t score, which is my test statistic, is negative 0.96. So it's equal to negative 0.96. My p-value is equal to, I think they asked for that as well, is 0.169, 0.1169. That's the p-value, and state the conclusion. So this is how we do it. We look at this value here, and then I say, is this less than or equal to or greater than my significance level? Well, this is definitely greater than my significance level. So what I do in that case is if it's greater than my significance level, then I fail to reject my null hypothesis. That means it could be good. That means it could be good. It could be equal to this value. That means that I'm not going to support, if this could be good, so I'm going to say, now I'm not going to support this alternative hypothesis. And since the claim here, less than, matches the alternative hypothesis, I'm not going to support that claim. So what am I going to say about the conclusion? I'm going to say there's not enough evidence to support the claim that the mean comes from a population that's less than 6.0 or something to that effect. So that's where we're going with this. All right. And how does that work kind of realistically? Remember, the confidence interval method, which we learned in chapter 7, is equivalent to the hypothesis method in chapter 8. So what that means is if we had a number line here and we had, so here's 6.0 on the number line, and now we just found a confidence interval, right? So here's 6.0. The 5.85 is somewhere over here, right? So here's 5.85. And what we were doing was we were building an interval around that 5.85 of where we thought that the true population values fell. Now, if we went over the 6.0 in our values, then that means this, that it could have been 6.0, right? That it could have been here. But if we didn't go over, then we would have rejected that null hypothesis. But in this case, we did go over. That means that our interval went over. It included values that had 6.0 and possibly over in them. So that's why we failed to reject it. So we said, oh, no. We believe that there are possibly, or that the population mean, could possibly 6 and maybe even higher. The mean could be 6 or higher, so we're not going to support that claim that it's definitely less than 6, and that's how we need to look at it. If we had had a smaller interval around it, something like this, that included all values that were less than 6, then we would have come back and said, no, we support that claim. And how could we do that? Well, in this case, look at our p-value. Our p-value is 0.169. That means, and we didn't use the significance level in any of our calculations here, right? So that means that even if we use the 0.1 significance level, which is our least strict significance level, that it still wouldn't change our conclusion, would it? Because this is going to be greater than any normal significance level that we're going to use. So this is just a bad claim altogether. So in order to make a claim that's going to hold water, or in order to kind of get past the statistical community here, we're actually going to have to change the claim. Maybe we're going to have to change it to less than 7. Or maybe we're going to have to change it to less than 6.5. Maybe we're going to have to play around with the numbers a little bit and then, see until we can get that p-value to less than something that, we can, less than 0.05 or less than 0.01 or however low we need to get it until we feel comfortable about that claim. All right. I hope that helped a little bit, and I hope you have a great rest of your week. Thanks.